Okay, cool. We are now recording, so we're good to go. Again, it's 11 o'clock, so we will go ahead and get started. So this last lecture, we started looking at exponential functions. So now we've kind of at this point 3 different kinds of functions in this class. We've seen linear, we've seen quadratic, which linear and quadratic have expanded to just be polynomial in general, and then we've now seen exponential. The last type of function that we will be looking at in this class, which is coming up within the next couple of lectures, is the logarithmic function. So that's coming up. We're just, not quite there yet. So as far as the homework is concerned, I realized that I goofed, but it really didn't make too much of a difference. The very, very last question, number 87, you guys couldn't do because we haven't done continuous compound interest yet. So if you tried to do 87, you probably were a little confused as far as which whether you should use simple interest or compound interest. The answer is actually neither. Supposed to use continuous compound interest, and that's okay if you tried it and you plug numbers in. If you plug numbers in, you would have gotten an answer anyway, and that's totally great. I'm just letting you know that technically the correct answer would have been from continuous compound interest, which you wouldn't have been able to do. Again, sorry about that. I copy pasted the questions from a previous homework, threw it into here, and it completely escaped my mind to check that, oh yeah, one of these should have continuous compound interest, and we haven't covered that yet. So questions 23 through 70 you should be able to do, and then 87 you'd be able to do after the next lecture. So don't worry about 87. So who has questions about any of the first questions, the ones before it? So 23 through 70. Any particular questions on that? Okay, let's see. Number 23. And then also 31. Sure. Okay. So 23 was quite literally just evaluating your ability to plug into a function. So let's take a look at what we're given. We are given the function h of x is equal to 2/3. I'm going to clean that up a little bit. 2/3 to the 2x minus 1. And this is absolutely still an exponential function. Although there's some stuff going on in our exponent, the input is being multiplied by 2. We're taking 1 away from it. It's still an exponential function. It's just not the basic one that, we talked about at length for, about 10-15 minutes yesterday regarding the properties. But it's still an exponential function. So what we have to figure out is we have to evaluate h, or our function, at specific points here, or at specific inputs. So we have to find h of 3/2 and also h at -1. Okay, so remember, anything that's inside here that I'm underlining in green, well, these are inputs. These are just things that you're plugging into your x value. So whenever you have an input, or whenever you have something in this form, h of some number, that's always going to be indicative of you plugging that number in wherever you have your variable. So wherever there's an x, you're plugging in 3/2, or later on, wherever there's an x, you're plugging in -1. So let's do h of 3/2 first. So h of 3/2. Okay. So Jeanette, if you can help me out, I just want to get this in the correct form. Help me plug in 3/2 wherever there's an x in my function here.
2/3 times 2 3/2 minus 1.
Perfect. Okay, and just to clarify, Jeanette said times, and that might have just been a little brain skip, and that's totally okay. So it's just, remember, this is your exponent, right? So you're not multiplying 2/3 times this piece. The piece that's underlined in black here is your exponent to 2/3. But yes, absolutely great. So let's go ahead and simplify this down. So basically, we just need to simplify our exponent and then see what happens to 2/3 after that. So we handle multiplication first, just like you would if it wasn't an exponent. What's 2 times 3 halves? Well, the 2 on being multiplied and the 2 being divided are just going to cancel out. So now what we have is we have 2/3 to the 3 minus 1. And what's 3 minus 1? Well, that's just 2. So we have 2/3 squared. And how do we handle an exponent being applied to a fraction? We apply that exponent to both the numerator and the denominator. So 2 squared and 3 squared. And so we get 4/9. And that's our final answer for the first one. Okay, so really not that bad. All you're doing is you're just taking your input, plugging it in wherever there's an x, and then simplifying down. 2 times 3 halves gives you 3, and then 3 minus 1 gives you 2, and then you just have 2/3 squared, and when you apply it to the top and bottom, you get 4/9. Any questions on this? So, because again, the next one is going to be the same thing, but just want to make sure that we're good with this one. Okay, cool. So we'll go ahead and keep going. So h of -1, that's the next piece that we have to find, right? So once again, your base is 2/3. You're starting with 2 times x, right? So that's 2 times -1 minus 1. So 2 times x minus 1, 2 times -1 minus 1. Okay, simplifying this down, we have 2/3. Our base remains unchanged. 2 times -1 is -2 minus 1. So now we end up with 2/3 to the -3, right? So -2 minus 1 gives you a -3, and that's now your exponent, right? And I always recommend doing this in 2 steps. Handle the negative sign first, and once you've handled the negative sign, then do the actual exponent, right? You can do it in 1 step if you're comfortable enough, but I just recommend doing it in 2 steps. That way you are positive that you're not making any mistakes. So let's handle the negative sign first. What does a negative sign imply when we're talking about exponents? Anybody? What am I doing with if I have a negative sign in my exponent? You guys know this. I bet you do. Just be confident in your answer. Let's see. Yes, you flip the fraction, exactly, right? So instead of 2/3, if we have 2/3 to the -3, when we handle the negative sign, we're flipping the fraction. We're flipping it on its head. Instead of it being 2/3, it's now going to be 3 halves. The 2 goes to the denominator, the 3 goes to the numerator. So instead of it being 2/3 to the -3rd, we now have 3 halves to the +3. And now all we have left to do is, well, we have 3 halves to a number. We took care of the negative sign. We just distribute that exponent. Once again, we distribute it to the top and to the bottom. So this is the same thing as 3 cubed over 2 cubed. And when we simplify this down, 3 cubed is 27. 2 cubed is 8. So we get 27/8. And we're done. Okay, so once again, the process, you take your input. Your input in this case was -1. You're plugging -1 in wherever you have your variable, right? In this case, this is an exponential function, so your variable is going to be in the exponent. So you plug -1 into your exponent. You simplify the exponent down. So in this case, we got a -3. And then you just handle it however you need to handle it. In this case, how I did it was I handled it in 2 steps. So I handled the negative sign first. So I went from -3 to 3 halves to the +3. Because all I did is I flipped it on its head, and then I applied the cube to both the top and to the bottom, giving me a total or a final answer of 27/8. Any remaining questions on this? Okay, sounds good. All right, so let's move on to number 31. So questions 27 and 31 were both actually pretty unrelated to the topic, to exponential functions. 27 and 31 were really just, do you know your exponent rules? That's all these were asking. So let's look at 31. So we have let me zoom in. I don't know what happened there. Okay. So we have a to the square root of 3, and this is being raised to another exponent of 12. Okay, we have an exponent rule for this. Whenever we have a base being raised to an exponent, being raised to another exponent, we have to do something with the exponents. We know that our base is going to stay the same, so our base is a from before, so our base remains as a. And now something's going to happen to our exponents. We do some operation between square root of 3 and square root of 12. So you think to yourself, okay, well, there's realistically 4 different operations that we, could possibly do, right? You could either add them, you could subtract them, you could multiply them, or you could divide them. From what we know, well, if we're talking about our exponent rules, we know one of our exponent rules is if we had this, for example, hypothetically, well, this tells you keep the base the same and you add them, right? So this is your addition of exponents. So if this one is your addition, and obviously this looks very different than that, then okay, well, then the top one, you're not adding your exponents, right? So, okay, this one's out. You're not going to be adding your exponents. That operation is out. Then your next one is, okay, well, what about subtraction? Well, subtraction of exponents only occurs when you have a division of the same base, right? So if you add a to the square root of 3 over a to the square root of 12, then you would keep your base the same, and you would subtract your exponents. So once again, notice we don't have a division of the same base here, so you don't need to subtract any exponents. Subtraction is not the operation that you're going to be doing here. So that one's also out. And last but not least, division. Well, we don't have a rule for division of exponents. There's not a single exponent rule that we have that involves your exponents dividing each other. So division is also out. So all that leaves is just multiplication. So if you forgot, try to use process of elimination to figure out what operation you're actually doing with your exponents. So in this case, yeah, we're going to have square root of 3 times square root of 12. Okay, now we simplify this down. Well, remember, and this is not just remembering your exponent rules, but also remembering your rules when in regards to radicals and roots and such. When we have the same index root, we can multiply the things that are inside together. So what I mean by that is, remember, your index of a root is always going to be this number that's right outside. And those aren't zeros, that's just circling where your index would be. And notice that the index is not present, right? So when you don't see an index, what you should automatically think is this is a square root, right? A hiding index in front of a radical means that index is really a 2. So because they match, you have a square root for 3 and you have a square root for 12, you can keep it a square root and you can multiply everything inside together. So we keep it a square root, and we now have 3 times 12 underneath 1 square root. So simplifying this even more, we now have a to the 3 times 12 gives you 36. And then finally, when you take the square root of 36, you get a to the 6th power, and you're done. It is now simplified. Does anybody have any questions? Again, the first step is purely your exponent rules. If you have any number raised to any base, raised to a second base, I'm sorry, if you have any base raised to an exponent raised to a second exponent, you just multiply the exponents together, and you keep the base the same. So our base was a. So again, our base was a, and it was raised to 1 exponent and then a second exponent. So we multiply the 2 exponents together and keep the base the same. And then using our rules of radicals, we know that we can actually combine the 2 radicals, multiply the insides together. And when we do that, we got a perfect square underneath of a square root, which worked out really nicely for us. And we could just simplify it down. Square root of 36 is just 6.
I have a question.
Sure.
This is more on number 27, but if you were to, it kind of has to do with it. So if you were to subtract, because wouldn't you have to subtract the exponents pi minus pi? Wouldn't that be 0?
Yep.
So would your answer for 27 be 2 to the 0 power, which would be 1?
Well, let's do it. Let's see what happens. No, it's fun. So we have, okay, so we have 8. Oops, sorry, we have 8 to the pi, and we're dividing 4 to the pi, right? Okay, so what the question was, wouldn't we just end up getting 2 to the 0 power? Well, before you can actually do this, you have to ask yourself, well, our exponent rules only allow us to do the exponent rules when the base is the same. Do we have the same base right now? No, right? We have an 8 and we have a 4. So we can't jump immediately to the exponent rules. What we have to do is we have to change the base of these numbers so that way we have the same base, and then we worry about the exponents later, right? So luckily for us, both 8 and 4 are powers of 2. We can change 8 to be a power of 2, and we can also change 4 to be a power of 2. So let's ignore the pi's for a second. Let's think about 8 in terms of 2 and 4 in terms of 2. So the reason I'm doing this is I want to have the same base. I want to have 2 and 2, right? If I have the same base, then I can do my exponent rules, and we can go from there. So what I want to figure out is what my exponents are right here. So 8 in terms of 2, well, that's just 2 cubed, right? We know that 2 times 2 times 2 gives you 8, so that's 2 cubed. Let me write this in black, sorry. So that's 2 cubed. And then 4, similarly, we know 2 times 2 is 4, so that's 2 squared. So, okay, great. So now we have 2 cubed and we have 2 squared, so we can replace this, right? So this is really the same thing as 2 cubed to the pi, and we're dividing 2 squared to the pi. Okay, and what did we just talk about as far as exponent rules? When we have a base raised to one exponent, raised to a second exponent, you can just multiply the exponents together, right? So this is really 2 to the 3 pi divided by 2 to the 2 pi. Okay, fantastic. We now have the same base, right? So we have a 2 here, we have a 2 here. They're being divided. So if you wanted to change how this looks, you would have 2 to the 3 pi divided by 2 to the 2 pi. And now what is one of our exponent rules? Well, we just talked about it a little bit in the question, but what we're going to do is we keep our base the same and we subtract the exponents, right? So 3 pi minus 2 pi. And your final answer here, you keep your base the same, it's still 2, and now you just have 3 of something minus 2 of something. Well, you're just subtracting the coefficients, right? So it's the same thing as if that were just an x, a y, whatever the case may be. Sure, pi is a number, but for all intents and purposes, you could treat it like a variable here. So 3 pi minus 2 pi should just give you 1 pi, and I'm just going to omit that coefficient and just say pi. So your final answer here is 2 to the pi.
Thank you. And if
Yep.
we have time before the quiz, could we do 35A?
35A, yes, that's sure. And I saw Keji's question of 39. Keji, I'm actually going to hold off on 39 because 39 is just sketching. And that's all you were doing was you just pick inputs, right? And then you plug your inputs in, right? So like in the lecture video, I made a table of inputs by, I had like X, and then I also had f of x here. All I did was I just picked a set of numbers. So I went from like -2 to +2, and I plugged those in and see what I got. That's the same thing that I would do here. So I would plug -2, just a small set of numbers in just to get some points. And then when I have some points, I would, plot that on a graph. So 39 is really just, showing you what an exponential function is going to look like. It's really not testing any of your skills, or at least it shouldn't be. I imagine that a lot of you guys by now are okay with graphing. If you're not, then please see me on the side, because 39 really shouldn't be too tricky. So since that's the case, I'm just going to jump to 35, and if we have extra time, I'll double back to 39. Okay, Keji? But before I do that, again, I just want to make sure that we're all good with this one, because this one took some manipulation. This one wasn't straightforward. You had 8 to the pi divided by 4 to the pi, and we can only apply our exponent rules when we have the same base. So if you didn't realize that, then you would have probably been stuck right at the beginning. You probably wouldn't have been able to get any further. So what you had to realize is that you could change both 8 and 4 to be bases of 2 and then go from there. But once I gave you, once I said that, hopefully you guys see it now a little bit more clearly that once you change things over to base of 2, things kind of fall out a lot more neatly. So if you have any questions on this, please let me know right now. Okay, guess we're going to move on then. Fantastic. So 35a, we have to find a function in the form of f of x is equal to c times a to the x. And we are given two solutions to this function. So the solutions that we're given are 1, 1, and also 2, 5. So 2, 5. Also, just real quick, I just want to mention this. You guys are going to start your quiz a little bit later today because the quiz shouldn't take you that long. So I'm just going to have you guys start at 11:30 instead of the normal 11:25. So don't worry if you think I'm going over because, you guys are just going to have slightly less time for it. It's a shorter quiz than most others. So in any event, so we have to find a function in this. Given the two solutions, 1, 1 and 2, 5. So if you guys watch the lecture, you recall that the entire idea here is you have two unknowns. Yes, technically you have three variables, right? You have c, a, and x, but you're not ever actually solving for x, right? X is always going to be part of your function. It's always going to be built into your function because what is a function? A function implies that you have some unknown input and then you get some unknown output, right? So x is just going to be ingrained in your function. So realistically, you're actually only solving for two variables. You're solving for c and you're solving for a. So what you're going to do is you're going to take these points here and you're going to solve for them one at a time. You'll solve for c first, generally, and then you'll solve for a after the fact once you figured out what c is. You could go in the opposite order, and it won't matter. I'm just letting you know that that's your general game plan. You solve for one variable, and then once you have a value for that variable, you go and solve for the second one. So with that said, what we're going to do here is we're going to take our input and our output. Remember, that's all an ordered pair is, right? An ordered pair says, okay, well, the number on the left of the comma is an input, and the number on the right of the comma is my output, right? So the output is going to be f of x. That's this piece. And the input is going to just be the x itself. So all I'm doing is I'm plugging in 1, 1 into the function of this form, and we're going to solve for c and a. Or, one or the other first, and then we'll solve for the other one. So if I have, again, f of x is equal to c times a to the x, well, my output is 1, so f of x is equal to 1, so that's my left-hand side. And then I have c times a to the, and then, again, my input, my x, is also 1, so a to the 1. And simplifying this, we have 1 is equal to c times a. And now it's up to you. Whichever way you want to solve for. If you want to solve for a first, that's fine. I generally solve for c first just out of habit. Just out of the number of times that I've gone through these problems. I generally solve for c, and then I go back and solve for a. So solving for c here, well, all that means is I isolate c, right? When you're solving for a particular variable, if you have multiple variables in your equation, you're just moving all the other variables that you don't care about to the other side. So if I'm isolating c, I'm just going to divide by a on both sides. So dividing by a on both sides, I get 1 over a is equal to c. So notice we didn't actually get a particular number for c, but we do have a value for it. C is equal to 1 over a. That's for fact. We know this to be true. So now what we can do is we can set this up again. So f of x is equal to c times a to the x. And now we're going to use our second input, the 2, 5. Well, our second solution, I should say. Second input being 2 and second output being 5. And this time, we know what c is. So we can plug c into our equation, and we'll be able to solve for a. So our output is 5. So that means f of x is 5. My left-hand side is 5. That's my output. That's what it's always going to come out to be. And my input is 2. So I have a to the 2, or otherwise known as a squared. And then once again, we know the value of c, which is 1 over a. So we can plug this in for c. That is our value, 1 over a times a squared. Okay? And now you can, however, you're comfortable solving this, you can either throw the a squared on top. So you can say this is 5 is equal to a squared divided by a, or alternatively, and this comes back to exponent rules once again, 1 over a is the same thing as a to the negative 1 power, right? If you guys remember, if we went backwards, that negative 1 power implies that you have a fraction, a over 1, right? You just flip it on its head, so that's the same thing as 1 over a. And so you would have a to the negative 1 times a squared, and however you figured it out, it'll come out to be the same, because exponent rules say, great, you have the same base, you're multiplying them, you add them together, right? So a to the negative 1 times a squared is the same thing as a to the negative 1 plus 2. And when you add them together, you just get a to the first power, which is just a. So, hooray, a is equal to 5. And again, just showing the other way, if you kept it as a fraction, you would have a squared divided by a, but a squared divided by a, well, you're just canceling out one of the a's, right? So your a on the bottom cancels out with the, one of the a's up top, and either way, you're left with 5 is equal to a. And now, great, we have an answer for a. We have a final value for a. A is equal to some number. That's perfect. Now what we have to do is we have to figure out the final value for c, right? We got a value for a, and now we go back and we figure out what c is. And remember, c is equal to 1 over a, but we know what a is, so c is equal to 1/5. And you have now figured out your two values, so you can finally write your function f of x is equal to, and remember it was supposed to be in the form of c times a to the x, so f of x is equal to 1/5 times 5 to the x power. Any questions on this? Technically, there is one final step that you could do to really simplify this, and I'll talk about that in just a second, but I don't want to confuse anybody on the process before this. So is everybody good with up to here? Again, your idea is it has to be in the form of f of x is equal to c times a to the x. So every time that's how you're starting, right? You set up your equation or your function with this form, right? And now what all you're doing is you're taking your inputs and your output and plugging it in directly into your function. Your output is always going to be what your f of x is, and your input is always going to be what your x is. And then you solve for one particular variable. It really won't matter which one you solve for. Solve for, in general, try to solve for the simpler one first, so that way you could solve for the more complicated one later. In this case, they were both equally simple, right? It was just c to the first power times a to the first power, so it really didn't matter which one you solved for. So I solved for c here, and then I used my second given point, or second given solution, to figure out the value of a, which then led me to the final value of c, and then we could write it like this. Again, any questions on this before I do the final simplification here? Because there is one more simplification that you could do. Okay, so the final thing that you could do here, if you really wanted to simplify it in its most simple form, is remember, again, exponent rules, right? 1/5. 1/5 is the same thing. If we rewrote this again, using our exponent rules, 1/5 is the same thing as 5 to the negative first, right? We know this to be true. We know that any fraction, you can always turn into the number, so in this case, 5, the number from the denominator, and then, to some negative power. So in this case, since this was 5 to the first power, you could flip it on its head and make it 5 over 1, and just make the power negative, so 5 to the negative first. And it's still being multiplied by 5 to the x. But what is our other exponent rule? Our other exponent rule is when you have the same base being multiplied together, you could just add the exponents together. So 5, you keep your base the same, and now you just add the exponents together. But adding the exponents together, you have a positive x plus a negative 1, which is the same thing as x minus 1. So in reality, what I just circled, this is the most simplified version of the function. However, if you got to what I'm about to circle in green, if you got to this point, I wouldn't take any points off. That's, you did your job, you found the values, you got it in that form, and that's great. Because again, the question did ask you technically to get it in this form with some coefficient and then a to the x. It did not ask you to put it in the form that I have circled in black here. So if you did get it like that, congrats, you really know your stuff. And if you didn't, that's totally fine either way. Because, again, this is what the question was asking for. All right. So any questions on this? Because I know the quiz just came up on Blackboard. I just want to make sure you guys have no other questions. We're good to go. Yes? Okay. All right, guys. So the quiz just came up on Blackboard. Go ahead, take your time with it. You have the remainder of the class time for it, so about 20 minutes. And then the normal thing, just scan it, get it back to me within 10 minutes of class. Okay. I'm going to stop recording now, so give me 1 second.